Okay, so in this video we'll talk about another method of integration called trigonometric substitution. And this is different from the previous video where we looked at which substitution we need to make if you have integrals with powers of sine and cosine. Here we're going to look at integrals that don't actually have trigonometric functions right from the get-go. But as a technique to evaluate these integrals, we're going to be introducing trig functions. And we'll see that that actually makes these integrals easier to evaluate. So I'll start with an example here. Evaluate the integral from 0 to 1 of the square root of 1 minus x squared dx. And, well, this is actually pretty simple, right? You just have to recognize that this is the quarter circle with radius 1, right? And so we know that this is just pi r squared over 4, so that's 1/4 pi, right? Just recognizing it as an area. And so in this case, we didn't have to deal with, finding an antiderivative of the square root of 1 minus x squared. So what if it were an indefinite integral? Right? So now we're actually looking for a function, right, or a family of functions that represents the antiderivative of the square root of 1 minus x squared. And you could try u equals 1 minus x squared as your substitution here, but that's not going to work here because you don't have a 2x or even just an x term to stick together with your dx. Right? So that's not going to work. I mean, you can try if you want. Instead, what I'm going to do is the following, and it's going to seem weird at the beginning, but just bear with me. I claim that what's going to work here is if I make the substitution x equals sine theta. And here you immediately see that it's a different kind of substitution from what you're normally used to. Right? Instead of saying something like u equals 1 minus x squared, where you're setting your new variable to be a function of x, which is the variable in your integral. Now we're setting x, which is this x inside your integral, to be a function of your new variable, what we're transforming to. And so sometimes this is also called an inverse substitution because we're going the other way. Right? We're starting from x and saying, well, I'm going to let x be something. And this, again, might look to you that we're making it more complicated. Right? So let's just try this and see what we get. If x is equal to sine theta, well, remember, whenever we're making a substitution, we need to find dx, or d theta in this case. And so the derivative is just cosine theta d theta. So let's plug everything in here. Okay, so x is sine, so it's 1 minus sine squared. Dx is cosine theta d theta. Okay, right? So now, oh God, we have sines, we have cosines, we have square roots. How do we deal with that? Well, look, the nice thing about making this specific substitution here is that 1 minus x squared, which is 1 minus sine squared theta, we know what that's equal to. That's just equal to cosine squared theta, right? Because of our classic identity, sine squared plus cos squared equals 1. And in fact, this is what makes this substitution work here. Because now, this is just the square root of cosine squared theta times cosine theta d theta. Okay, so what's the square root of cosine squared? That's the absolute value of cosine. And in fact, we can restrict our substitution for theta to just be in the first or fourth quadrant. And if we do that, that actually means that cosine is just positive, right? So we can get rid of the absolute value sine. And now it's just the integral of cosine squared. And well, no, this is the reason why, or this is a reason why we talked about the trigonometric integrals in the previous video. So now we can evaluate this. Cosine squared is 1 plus cosine of 2 theta over 2. And this is now easy to evaluate. That's just 1/2 theta plus sine 2 theta over 4 plus c. Right? And now we have an antiderivative, although it's not yet in terms of x, but we have an antiderivative. And so now what you'd like to do is to change this back to a function of x. And well, now again, this comes into play. When x equals sine theta, then theta can be thought of as sine inverse of x, because again, we've restricted your theta to be between minus pi over 2 and pi over 2. So this is 1/2 sine inverse of x. Okay, how about sine 2 theta? Sine 2 theta is equal to 2 sine theta cosine theta over 2. I mean over 4, so we still have over 4 there. So we're really just plugging in x for sine theta. And for cosine theta, it's the square root of 1 minus x squared. And we're done. That's the antiderivative of this integral. And you can actually check. Well, for one, you can take the derivative and show that you get the same thing back, square root of 1 minus x squared. Or, one way to check, to do a sanity check here is to go back to our definite integral, plug in a 0 and a 1, and then subtract and show that you get exactly 1/4 pi. Okay. So, how did I know to do this? Right? That's probably the question that's in your mind right now, is that how did I know to do x equals sine theta as my substitution rule here, right? As an inverse substitution. And really that just, again, comes from the use of this trigonometric identity. I saw that inside my integral, I had an expression of the form 1 minus x squared. So if somehow x could be replaced by sine, then 1 minus x squared just becomes cosine squared. And you take the square root, it's just cosine. And that's exactly what happened here. Right? And so it's this being able to recognize the expression and mapping it to either this trigonometric identity or another one that I'll show you in the next example that allows you to decide which substitution to make. Okay, so let's look at this one for instance. It's also a square root of something, and then inside you have x squared plus 4. And, well, if you do x equals sine theta here, you're going to get sine squared theta plus 4, right? So that's not really a trig identity, right? So let's write down the trig identities we know of. We have sine squared plus cos squared equals 1. And, well, as a corollary to that, if you divide the whole equation by cosine squared, that becomes tangent squared plus 1 equals secant squared. Right, and so this gives us a clue here, right? Because in our integral, under the square root, we have x squared plus 4, which kind of looks like this, right? It's something with a variable, we're squaring it, and we're adding a constant. In the previous integral, it was 1 minus x squared, right? So we were able to write this first identity as cos squared equals 1 minus sine squared. Well, okay. So, knowing this, that it kind of matches tangent squared plus 1 equals secant squared, what happens if we try x equals tangent theta as your substitution rule here? Okay. This gives me, well, first of all, dx is secant squared theta, d theta. But under the square root, this x squared plus 4 becomes tangent squared theta plus 4. And that's not what I want here, right? Because I need a tangent squared plus 1 to give me just secant squared theta. And then I can take the square root, and the squared term disappears. If it's tangent squared plus 4, that becomes, I don't know, like secant squared plus 3, right? Some weird expression like that. And taking the square root doesn't really simplify. So that 4 actually plays a role here in the sense that what I'm going to do is I'm going to set x to be equal to 2 tangent theta. Okay, so y2. So dx becomes 2 secant squared. And now x squared becomes 2 squared tangent squared, right? Or simply 4 tangent squared theta. Right, so including that 2 in my substitution rule allows me now to write x squared plus 4 as 4, you can factor it out, times tangent squared plus 1, or simply just 4 times secant squared. Now I'm able to use this identity. So, okay, let's apply it. And I'm not going to bother with the bounds for now. So remember, if you have a definite integral, you can simply work on the indefinite integral first and get an antiderivative. So that's what I'm going to do here, because I want to take the antiderivative and substitute back all the way to x from theta. So let's do the substitution to theta first. This becomes, so the square root of x squared plus 4, the square root of 4 secant squared theta. And outside I have a secant squared theta d theta. This becomes 2, and now it's the absolute value of secant, right? But in fact, we can restrict our interval here for tangent so that we also guarantee that secant is positive. So in fact, the correct interval here is also going to be the first and the fourth quadrant. So theta in between, well, strictly in between minus pi over 2 and pi over 2. And that just allows me to write 2 secant cubed theta d theta. And well, I did say that I was going to compute this antiderivative all the way to the end and plug in x back, but I'm actually not going to do that. The integral of secant cubed is actually a nice exercise for you to think about. It's a bit involved, but I'll actually leave that for you to try doing yourselves. But again, the point here was that recognizing that it's x equals 2 tangent theta was a substitution rule, precisely because under the square root here we had x squared plus 4. Right? In fact, I can write 4 as 2 squared. So writing 2 and tangent theta inside here allows me to make use of exactly this trig identity to simplify and remove the square root. And just to summarize here, in fact, you don't even need to see necessarily a square root before you can try applying one of these substitutions. If you see a form or an expression with a squared minus x squared, it means, well, maybe we can use the identity 1 minus sine squared equals cos squared. All right, so a here is a constant, right? It's a number. In the previous example, a was 2. And so if we want to use 1 minus sine squared here, this means we need to use the substitution x equals a times sine theta. Right? And because now this allows me to do a squared minus x squared is now just equal to a squared cosine squared. A squared plus x squared, if I see something like this, the corresponding trig identity is 1 plus tangent squared equals secant squared. Right, so a is your constant, so I have the 1 on the left, x variable, so I'm making the substitution, x equals a tangent theta. And now this is going to give me a squared plus x squared equals a squared secant squared theta. And finally, if it's x squared minus a squared, well, I can actually rewrite this second identity to be secant squared minus 1 equals tangent squared. Right, and now it's x equals a times secant theta. But now your theta is actually going to be restricted to be in the first quadrant or the third quadrant. So that tangent remains positive, and you can get rid of whatever square roots you have without having to deal with absolute values. Okay. And so just to give you an example here, down here you have square root of 9x squared minus 1. Right, so it's in that same kind of quadratic form. So what do you do? Well, it's not exactly x squared minus a squared, right? It's a constant times x squared minus another constant. But what you can do is to simply factor out the square root of 9 first. That's a 3, so this is 3x to the 5th power square root of x squared minus 1 over 9. And now this is in the form x squared minus a squared, where a is 1/3. Right, so we're going to use the substitution. X equals 1/3 secant theta, which gives me dx equals 1/3 secant theta tangent theta d theta. X squared minus a squared is equal to just 1 over 9 tangent squared. And just plugging everything in, now you're going to get an integral in theta. And you have 1/3 secant to the 4th power, and so on and so forth. Right, and a bunch of stuff will actually cancel here, and you'll end up with something that you are going to be able to integrate.